Now, previously, when we talked about how solids molecules are arranged, we learned that they can either be in a crystalline formation or in an amorphous formation. When they're amorphous, they're kind of just all jumbled together. There's no real organization, kind of like toys in a toy box, just get tossed in there. Crystalline is just the opposite of that. And this is when those molecules are in an ordered fashion, and we see this order repeated throughout the solid. So crystalline solids then are ordered geometric structures whose lattice points are occupied by atoms, ions, or molecules. Now we know that something is crystalline just by looking at it. If you look at like a quartz crystal, for example, if it hasn't been polished and it's like there's an exposed surface, you'll notice that it'll have flat faces and pretty sharp angles. And those flat faces and those sharp angles are evidence of crystalline, that it's a crystalline structure, that it has that geometric organization. Now, in order to study these solids, we use a technique called X-ray diffraction crystallography. Now, when we utilize X-ray diffraction, what we're looking for is we're looking for the creation of either constructive interference or destructive interference. And you might remember from Chemistry 1, we talked about this in terms of light waves. We learned that if light waves intersect in such a way that they amplify or intensify the light, that's what we would call constructive interference. But if the light waves interfere with each other in such a way that it diminishes the light, we would call that destructive interference. Now, with this crystallography, what we're doing is we're projecting parallel X-rays and letting them strike the planes of atoms within our crystalline structure. And depending upon how they reflect and the distances that are involved, this is how we're going to determine whether we have constructive interference or destructive interference. If we look at Bragg's law, this is a formula, a mathematical formula that will tell us a little bit about what's happening with our diffraction in our crystal. So let's look at the values that we've got here. So N stands for an integer. Now, in order for there to be constructive interference, this integer N needs to be an integer and not a portion of an integer. So we're looking for a number that's a whole number, like 1 or 2 or 20 or 41 or 2,186. We're looking for a whole number. A number that has a decimal or is a fraction is not an integer, so that would be telling us a different story. The lambda is the wavelength of our X-ray in this case. The distance that we're talking about, the D stands for distance, and that is the distance between the layers of atoms or molecules in our crystalline structure. And then our theta is going to be the angle that the rays come in at. So the angle that they're coming in at when they strike the surface, which should technically be the same that they are at when they are leaving the surface. So let's work an example using Bragg's law. So we're going to be given a lot of these values. So for us, it just becomes basically applying the math. So our problem says that when an X-ray beam of 154 picometers is incident on the surface of an iron crystal, it produces a maximum reflection at an angle of 32.6 degrees. Now we're going to assume an integral number of 1, and they want us to calculate the separation between the layers of iron atoms in the crystal. So we're going to take our Bragg's law, which is the formula right here. And we know from looking at what we're given that N is going to be equal to 1. We're given our lambda right here, 154 picometers. We know that the angle is going to be 32.6 degrees. So if we plug those numbers in and do the math, we can figure out that the distance ends up being 143 picometers. It's just that simple. Now, in order to get these crystal structures, what ends up happening is a substance that is liquid at a very high temperature is allowed to cool, and to do so slowly. And when this substance is allowed to cool slowly, the particles that are in the liquid are going to rearrange in order to give the maximum attractive forces, because you might remember that Mother Nature likes to have low energy systems. So as this crystal structure cools, it's going to rearrange to give that maximum amount of attractive forces. And that's going to be the way that this structure minimizes energy. And the arrangement of the particles in this organized fashion is called the crystal lattice. Now, because the crystal lattice has these units that are repeating, we have to have a way to designate that. So the smallest unit that shows the pattern of arrangement that we see present in all the particles, this is what we would call the unit cell. So if we look at our picture here, we can see that this square with a circle in it is our unit cell. So we have these unit cells arranged in a crystal lattice. So we have to have a way to talk about these lattice works and these unit cells. So let's get some language out of the way. So unit cells. Unit cells are going to be three-dimensional. They're usually going to contain a couple of layers of particles. And they're going to be repeated over and over throughout the substance, and it is the repeating patterns of these unit cells that give the macroscopic appearance to our crystal. So it's the repeating patterns of these unit cells that are going to give us those flat surfaces and those sharp angles that make up our crystalline structure. Now, if we start anywhere within our crystal and we cut it open and look at it, we're going to see these unit cells throughout. It doesn't matter where we go within our sample of our crystalline structure. We're going to see these unit cells replicated throughout it. Each particle in the unit cell is going to be called a lattice point. And lattice planes are planes that are going to connect equivalent points in unit cells throughout the lattice. So basically what we mean is that if we have a corner here, it's going to connect to an analogous corner on another unit cell. If we have an edge here, it's going to connect to another analogous edge in another unit cell. Now, because these unit cells are repeated throughout the crystal, there's a couple of concepts that we need to address. And one of them is how they go about making contact with other unit cells and how efficiently are they packed together. So the number of other particles each particle is in contact with, this is called a coordination number. The higher the coordination number, the more interaction the particle of that unit cell is having. And that means the stronger attractive forces there are that are holding that crystal together. Now, when it comes to packing efficiency, this is the percentage of volume in the unit that is occupied by particles. And the higher the coordination number, the more efficiently the particles are packing together. Now, there are many ways to, let me back up. There's a number of different types of unit cells that we could look at. And but for our studies, what we're going to look at is the cubic unit cell. We might take a pass at the hexagonal unit cell, but mostly we're going to stick to this one. So what do I mean when I say cubic unit cell? What I mean is that the orientation of the repeating pattern is going to be such that we're going to see 90 degrees at all the corners of this cell. The length is going to be equal to the width, which is also going to be equal to the height of this. That's what we mean by cubic. And if the unit is made up of spherical particles, then what we're going to see is that we'll have 1/8 of a particle at each one of these corners of our cube, which is what we see in this picture right here. So there's 1/8 of a particle, here's 1/8, there's 1/8 and back up here, one over here, there's another 1/8 down here, down here, down here, and then also in back. That's what we mean by that. Now, if we had a particle that was somehow located on a face on one of these flat surfaces, well, then we would see half of that face in our cubic unit. And if we had one located along the edge, not a corner, but just purely an edge, then 1/4 of each of those particles would be located within the unit. Okay, so let's kind of summarize what we have going on here. So we have 8 particles, 1 at each corner of our cube, which is what we see in this picture. And 1/8 of each of these particles, each one of these right here, lies within the unit cell. And what each one of those particles is contributing is 1/8 of its volume and 1/8 of its mass. So we have 8 corners times 1/8. So we could say then, let's come to this calculation right here, that 1/8 times 8 equals 1. So basically it takes all 8 of these to equal basically the volume of 1 unit. Now we had talked earlier about the coordination number, and we said the coordination number was the number of particles that one particle makes contact with in this unit cell. Now in this cubic unit cell, let's take a look at this one particle right there, and how many other particles is it making contact with? Well, here's one, and there's another one, that's 2, and then here's one, that's 3, and then here's 4, 5, 6. Now there is a particle way back there in back, but this one can't reach it because there's too much distance there. But this one particle has contact with 6 other particles, which means then we have a coordination number of 6. Now here's a chart that gives you some information that you're going to find useful as you move through this chapter. And what we see here, let's just start by looking at our simple cubic unit. Now we know that from our previous slide that the number of atoms per unit cell is going to be equal to 1 because we have an 8th here, an 8th here, an 8th here, an 8th here, and then another set of 8s down there, and there's 8 8s, and 1/8 times 8 equals 1. There's our 1. And we determine what the coordination number, there it is, and the edge length in terms of r is going to be 2r, which is 2 times the radius of each particle, because remember that an edge goes from the center out, so there's a radius on this edge, and then the other part of that radius is made up by this other particle, so that's where we get our 2r. And then we have something called the packing efficiency, which is tells us about, given a particular arrangement, how efficient is the packing of the particles. How much space and particle volume do we have? What is the efficiency? And in a simple cubic unit, we have about 52% packing efficiency. Now this chart is handy because it doesn't leave us out in the cold as far as trying to figure these things out for ourselves. So for example, they're giving us some information about the body-centered cubic, which means we have a particle here in the center. When we can see that we have 2 atoms that are creating this unit cell, the number of atoms that are involved here, because remember we have an 8th, an 8th, an 8th, and then that same series repeated on the bottom, plus now we have a whole one in the center, so we would have 1 comprising all the corners plus the one in the center. That gives us that 2. Any one particle is making contact with 8 other particles. And then we have some math. We're going to look at this on the next slide that tells us how we got here. And then we're able to see from the chart, at least, that we have 68% efficiency as far as packing. And then we have the same information replicated along a face-centered cubic unit. So the chart makes it easy for us to come here and grab the math and see what the efficiency is without having to do a bunch of fancy calculations to get there. So here we have our body-centered cubic unit, and what we saw on the previous slide is that we have the 8 in the corner plus the 1 in the center, and we're not including the mass of each one of these corners, we're just including an 8. So this is our unit right here. There's our unit. And as we saw, we have 1/8 of each particle in the corner, so that gives us 1. And we have this one right in the center, and it's whole, so that gives us the other one. So then that's how we come up with having 2 atoms in the unit cell. So that gives us a little bit about that. So let's move to the next slide and see what information is there. Now, as we've seen, this body-centered cubic is made up of 9 particles. We have an 8th, we have 1 in each corner. It's contributing an 1/8 of its volume, and then we have that one in the center. And the other thing that we can see here is at the edge of one of the units, we can calculate by using this value right here, or this amount times the radius. So what do I mean by that? Well, is this involves some geometry. So we could use this, but why not when we could use this? So we're going from the diagonal at the upper right of our cube down to the lower left, spanning the longest distance, and we're looking at the triangle that's made by going that way to this side, and then we have the actual side of our cube right here. So if we put that into the Pythagorean theorem, our hypotenuse, which is C, is equal to B, which is this right here, this length squared, plus the length of the cubic, which is this right here, also squared. And then we can do some algebraic gymnastics with that information. Substitute in our R, which is the radius, because remember the radius plays into this as well. And by doing all of this, we can see that the length of one side then is equal to 4 times the radius over the square root of 3. And this is in that chart, so you don't have to go through this every time you want to come up with it, but you can calculate it based upon using geometry. Now here we have the face-centered cubic unit, and what we have here are 14 particles, which means that we have 8 occupying the corners, and then we have another 6 half of our particles occupying the center, and they're providing the face part of our face-centered cubic. Now if we want to figure out how many atoms are in here, as far as total amount of atom volume, well, we know that the 8 corners are giving us that 1/8, and we can see that the faces are contributing half of their volume, and we have 6 of those. So when we do 8 times 1/8, we get 1, and then we do 6 times 1/2, and that's 3. That will give us 4 particles. So we have the mass, or I should say the volume of 4 particles represented in a face-centered cubic unit. And as far as the edge, what is the edge going to be? Well, we could do the mathematics, and they've done that formula for us, again using the Pythagorean theorem, looking at the hypotenuse, which goes from corner to corner, and one side, and the length, which in this case would be 2 lengths. 2 lengths squared, I should say. And it breaks down to 2 times the square root of 2, which we would multiply by the radius in order to get the edge of the length of the edge of this particular unit. And this is going to have a coordination number of 12. So when it comes to packing spheres, it's more efficient to offset each row in the gaps of the previous row than it is to line up the rows in distinct columns. So what you see here on the slide is that this one is sitting in the gap that was created by these two. So the second layer of atoms that can sit directly over the atoms in the first layer, this is called an AA pattern. So we can see the AA pattern here on the left, and we could have an AB pattern where in the second layer these spheres can sit over the holes in the first layer. So this is all about, keep in mind, all about packing these spherical shaped objects together as closely as possible. Now, when it comes to crystalline solids, there are a number of different types, and they can be classified based upon the types of particles that are in them and how those particles are being held together. And we can see on this slide some of the categories and some of the subcategories associated with it. And we're going to look at some of these categories on the next slide. So I'll give you a second here. So we have what are called molecular solids, And these are going to be crystalline structures whose composite particles are actually molecules. And you'll remember that a molecule is made up of at least two different types of atoms, so fairly complex composite particles in these structures. Then we can have ionic solids whose composite particles are going to be made up of ions, such as your calcium ions and lithium ions, things like that. Then we have atomic solids, whose solids are going to be composed of atomic particles. Now, how those particles are held together gives rise to the next three subcategories. So we can have non-binding atomic solids, and these are held together by dispersion forces. And you might remember that dispersion forces are the weakest of the intermolecular forces in that they are brief and fleeting. So we could have some of these crystalline structures held together with these non-bonding atomic forces, or as non-bonding atomic solids. Then we can have the metallic atomic solids that are held together by metallic bonds. And you might remember that metallic bonds are when you have metals coming together and their electrons, their valence electrons, dissociate from a specific nucleus and tend to be shared throughout the solid structure. That's the nature of a metallic bond. And then we have a network of covalent atomic solids where we have these structures held together by way of covalent bonds. And you'll remember that covalent bonds are when you have the sharing of electrons between atoms. Now, these crystalline structures are going to be arranged in what are called a lattice network, just like what we saw when we are first looking at ionic structures. And what that means is that these composite particles are going to be arranged in alternating patterns. So that's what we see when we're talking about the unit cells, those repeating patterns. And if we're looking at the subcategory of molecular solids, the lattice is made up of molecules. So the lattice sites, the areas that are being occupied by the composites, those are called lattice sites, what's going to be there are molecules. Now, in the molecular solids, these are held together by intermolecular attractive forces. I mentioned one on the previous slide. I said dispersion forces. They can also be dipole-dipole attractions, which is when you have some sort of a polarity in the molecules that are in these lattice sites having a little bit of polarity, and that's holding the structure together, or it could be by way of hydrogen bonds. And you might remember that the hydrogen bonds is going to be the strongest of these, and the dispersion forces are going to be the weakest, at least of the three that are listed here on the slide. Now, because the attractive forces in a molecular solid are fairly weak, because that is the nature of intermolecular forces, these structures tend to have low melting points. It doesn't take a lot of energy to pry the solids apart and make it liquid. So generally these are going to come in at less than 300 degrees Celsius. Now, when it comes to ionic solids, what we're going to have occupying the lattice sites are going to be ions. And these are going to be held together by the attractive forces of those of the charges on the ions. So you'll have positives attracting negatives, negatives attracting positives. And in this scenario, the attractive forces are going to be non-directional, and what that means is that every cation is going to be attracted to all the anions, and every anion is going to be attracted to all of the cations. Now, the coordination number, you'll remember, represents the number of close association or contact that one of the particles in the unit can have. So in the case of an ionic solid, this coordination number is going to represent the number of close associations of cations and anions in the crystal. And there's something interesting about this when it comes to the ionic solids, and that is when we have a high coordination number, which means that when we have a particle that's in contact with a lot of other particles, which will be of opposite charge, then we're going to have a really stable solid. and that's going to lower the potential energy of this particular crystalline solid. Now, the coordination number is going to depend upon the relative sizes of the cations and the anions in order to create this balance and as well as an optimal state. So if we think about the nature of anions and cations, what we might realize is that the anions, the negatively charged particles, are going to be larger than our positively charged particles. And the number of our negatively charged particles that can surround a cation or our positively charged particle is going to be somewhat limited based on the size of the cation, because a small cation means that it's going to limit the number of those large anions that can be around it. But a slightly larger cation could possibly provide more area for those negatively charged anions to populate around it. So then we can conclude from this that the closer in size the ions are, the closer in size that the cation is to the anion, the higher the coordination and the more stable that structure will be. So metallic ions are going to be held together with metallic bonds, and I described what those were just a moment ago. It's that general sharing of electrons throughout the structure without electrons being necessarily localized over one particular nucleus. And in this scenario, the strength of these bonds are going to vary with the sizes and the charges of the cations, which means the sizes and the charges of the metals involved. Now that means then that the melting points are going to vary. And the most closely packed arrangements of lattice points are going to be what we see here. So non-bonding atomic solids, what would make an atom not bond? Well, if it had a full valence shell, that'd be it. So when we're talking about non-bonding atomic solids, we're thinking about noble gases in solid form. Now these are going to be held together through very weak dispersion forces, and as a result they're going to have very low melting points. And they're going to tend to arrange the atoms in the closest packed structure. And that's either going to be through that hexagonal structure or through a cubic structure, because those tend to be the most efficient packing arrangements. And this is going to allow this structure to maximize whatever attractive forces may be there, and at the same time also minimize the energy in this solid. Now when it comes to the covalent atomic solids, we are going to have a scenario where we have some directionality. And what I mean by that is that you have, in a covalent bond or a covalent atomic solid, you're going to create those covalent bonds. And a covalent bond exists between two atoms. And in that sort of scenario, what's happening is that this atom right here is attracted and bonded to the one right next to it, which means that it won't have any attractive force necessarily to someone a little bit further away, which is what we saw in the ionic atomic solids, where you had a chlorine, for example, and maybe it was attracted to all the other positive cations that were right next to it, as well as the ones that were far away. That is a possibility. We don't see that with covalent atomic bonds because it's a real focused, directionally allocated attractive force at work. And because of this, these structures don't tend to form the closest packed arrangements in the crystal. So, and that's because this atom right here is only attracted to the one right next to it and no other. So there's not that drawing power across a larger area. But because of the strength of covalent bonds, these solids are going to have a higher melting point, generally, greater than 1,000 degrees Celsius. That's all right. And these networks that get formed have the possibility of affecting other physical properties that may be present in these structures.